In this video, we'll learn what makes a graph Hamiltonian. So first of all, there is something called a Hamilton path and also a Hamilton cycle. And the difference is pretty obvious because one is called Hamilton path and the other one is called Hamilton cycle. A Hamilton path is a path, but it has to touch every vertex of the graph. So it covers every vertex once. Every vertex once. And the once is not very confusing because in a path you cannot have repeated vertices. So the big point is that a path is special, it's called Hamilton, if it covers all of the vertices. And similarly, a Hamilton cycle is, probably you can guess what it is now, a Hamilton cycle is a cycle that covers every vertex once. Every vertex once. Of course, I should have said up here that this is a path that covers. Okay, so that's pretty straightforward. You just think of a cycle that hits all of the vertices of a graph, and that will be a Hamilton cycle. Now, we say that a graph is Hamiltonian if it has a Hamilton cycle. So if there exists a Hamilton cycle, the graph is Hamiltonian. So similarly, when we said that a graph was Eulerian if it had an Eulerian tour but not an Eulerian trail, the same thing is happening here. We say that it's Hamiltonian if it has a Hamilton cycle, not just if it has a Hamilton path. So let's take a look at a graph for which we can find a Hamilton cycle, so it will be Hamiltonian. So let's take a look at an example of a Hamiltonian graph. So this graph is actually called a cube for fairly obvious reasons. It looks like a nice box or cube, and what we can do is look carefully and find a Hamilton cycle. So it's going to be a cycle in this graph which hits every vertex. So for example, we might start at this top left vertex and go down and then across to the other face and then up using that edge. Now let's use this one, down again, use this edge, come back up and across, and hopefully it's clear. You can see that we've hit all of the vertices. 1, 2, 3, 4, 5, 6, 7, and 8. So this was a Hamilton cycle. Hamilton cycle, so the graph is Hamiltonian. Okay, now one thing to point out is that if you have a Hamilton cycle like this and you just remove the very last edge that we use, so we don't have this one being green, then the result is a Hamilton path. So a Hamilton cycle, I'm going to write Ham cycle, can be converted to a Hamilton path, by removing one edge. And the result is simply a path that covers all of the vertices. Now I'd like to point out the following observation. This graph that we have here is already Hamiltonian. So if I was to add in an extra edge between two of these vertices, the graph that results would still be Hamiltonian. So in general, if you have a Hamilton graph, you can add more edges in as long as you don't add more vertices, and you're guaranteed to still be Hamiltonian. So we can repeat that by saying that if G is Hamiltonian, then the supergraph, any supergraph G prime, so that means that G is in fact the subgraph of G prime, where G prime is obtained by adding new edges between non-adjacent vertices of G, then G prime is also Hamiltonian. And that is very straightforward because the Hamilton cycle that worked for G will still work for G prime. There are no new vertices that we have to worry about. So we can actually use this observation to show something useful. It should be very clear that the cycle on n vertices is Hamiltonian. That should be straightforward because find a Hamilton cycle, well, it already is a Hamilton cycle. It's a cycle that goes through all of its vertices. So that is straightforward, Hamiltonian. The cycle Cn is Hamiltonian. Now, if we take a look at the complete graph on n vertices, Kn, this is a supergraph of the complete graph. So this is like our G prime, where our Cn was our G. So this complete graph is obtained from the cycle just by adding more edges. For example, if you think of the cycle on 4 vertices like this, if you want now the complete graph on 4 vertices, all you have to do is keep adding edges until you've got them all. So by the observation above, observation, we know then that Kn is also Hamiltonian. Hamiltonian. Right? So keep that in mind. If you're wondering why is the complete graph Hamiltonian, it's because it has the cycle Cn as a subgraph of it, and that cycle is itself the Hamilton cycle. Now, unlike Eulerian graphs, there's no nice theorem. Like we had with Eulerian graphs, we said that a graph was Eulerian if and only if all the vertices have even degree. But there's no nice characterization that works for Hamiltonian graphs, and there's no nice algorithm either. But there are a few little examples that I think are fun to work through, and in fact, I think it's a good idea for you to try them on your own, and then in a different video, I'll post the solutions. So let me scroll down. I've written these out already. So these are 3 problems that I think are very nice to try. So this first problem is to show that the complete bipartite graph, which has one partite set on m vertices and the other partite set has n vertices, show that it's Hamiltonian if and only if the 2 partite sets have the same number of vertices, which is at least 2. So, and then the second problem is to give an example of a graph which has no Hamilton path, so let alone having a Hamilton cycle. Now, the third problem is similar to what we discussed. We said that if we have a Hamilton cycle, we can remove one of the edges. So we have some Hamilton cycle, and then this might be like the last edge right here. If we remove it, we're left with a Hamilton path. Can the reverse be done? Can a Hamilton path always be used to form a Hamilton cycle? Please explain your answer. So if you think yes, then explain why, give a proof for why. And if you think no, then give an example of a graph which actually has a Hamilton path but does not have a Hamilton cycle. And so those 3 problems are fairly straightforward, and I'll provide the solutions in another video.